The next concepts we're going to talk about are displacement, how much water the boat displaces, and draft, how deep the boat sits in the water. When we're talking about displacement, we're talking about how much water the ship displaces out of the way. So if we have a ship sitting in the water and the hull is watertight, of course, however much area or volume of the ship that's sitting in the water is how much volume or area of water is being displaced. Now, displacement is a pretty easy concept, so we can take this one step further and start applying buoyancy. Buoyancy is concerned with the specific weight, which is equal to the weight divided by the volume. The specific weight is illustrated by the Greek letter gamma. Since we're talking about ships, we can say that the weight of the ship, which we found in the center of gravity, divided by the volume of the ship. The volume of the ship here really is the volumetric displacement, the amount of the volume of the ship that is sitting underneath the water, and it's illustrated by this upside down triangle called del. The ship will float when the specific weight of the ship equals the specific weight of the water. So if we write this out, the weight of the ship divided by the volume of the ship, volumetric displacement of the ship, equals the weight of the water divided by the volume of the water. Now, of course, the denominators are always going to be the same because of this. Whenever the ship sits in the water, it will displace the same amount of water. To get the numerators to be the same, we have to think about increase in draft. So if a ship is just gently put into the water, its draft will continually increase until eventually the ship's weight is matched by the weight of the water. And then there we'll have flotation. There's other ways to think about this. If we have a container and we fill it directly to the brim with water, like so, and we put the ship in the water, the ship is going to increase its draft until its weight is equal to the weight of the water. However, since the container is filled to the brim, the water is going to spill out. If we measure this water, we can find the weight of the ship. Also, if we can't collect that water, we can find the weight of the ship by knowing its draft, which we can measure. From that draft, since we've designed the ship, we can calculate the volumetric displacement. We can multiply that by the gravity times the density of the water, and that will also give us our weight of the ship. Recall in the speed video that we talked about how a semicircular hull can have a deeper draft than a rectangular hull. Remember that we said the area of the semicircle was the same as the area of the rectangle, and we're talking about these cross-sectional areas right here. Now if we set the lengths of these hulls equal to each other, we can say that the volumetric displacement of the semicircular hull is the same as the volumetric displacement of the rectangular hull. And we can take this one step further and say the weight of the semicircular hull is the same as the weight of the rectangular hull. Now remember that we're talking about specific weight over volume. Since the volume of the rectangular hull is fuller, it reaches the needed volumetric displacement in order to float sooner than the semicircular hull does, and therefore its draft is not as deep as the semicircular hull. These are just some of the concepts for displacement and draft.